Well, thank you very much for inviting me. I'm very pleased to be here. I lived in Sydney for 20 years, recently returned to London, and I'm missing the place already. So Perth is nearly Sydney. It's near enough for me anyway. I was told I had to talk about the Water Cube, so I'm afraid the first half of the talk will be a bit about the Water Cube. But it is, I think, the project where we did the most intense collaboration between multiple disciplines, including architecture and various branches of engineering. And I'll do my best to try and describe why we took the decisions we took. It was a competition that we entered in 2003. So the work I'm going to describe happened 10 years ago. It's strange for me to think it was that long ago, but it was 10 years ago. And a group of designers came together from PTW Architects, from Arup as engineers, but also a firm in China called CCDI, who flew their architects down from Beijing to Sydney to join the design team for the competition. So it was a 10-week competition. And we did something quite unusual, which I'm surprised to be able to say to you I've never done before, nor since. I can't work out why I've never done it again. But what we did is we lined up the 10 lead engineers leading their disciplines to say on day one, what would success look like to them? What do they think a swimming centre should be from their discipline perspective? So the mechanical engineers said, look, it's about 14 degrees on average in Beijing during the year. But inside a swimming centre, we probably want water temperatures of about 28, especially in a leisure pool, to keep people comfortable. Therefore, it's a heating problem. And the best way of heating something is simply to absorb as much solar energy as possible, make use of it, and stop it getting out. So they wanted an insulated greenhouse. The electrical engineers said, well, from a lighting perspective, that'd be great too, but only if we diffuse the daylight. Because actually you get real glare problems if you get direct sunlight reflecting off swimming pools, and it becomes a safety issue. The next people who are highly influential and often are not even in the room at the beginning of a project were the acousticians. They said, well, that's all very well, chaps, but if we make it out of glass, it'll sound awful. Tiles, you need round swimming pools for hygiene reasons, reflect sound. Water reflects sound. If we make the roof and the walls also reflect sound, it will sound appalling, and it will just be an unpleasant place to be. And it was actually the acousticians who said, but look, there's this plastic stuff called ETFE, ethylene tetrafluoroethylene, recently used on the Eden Centre in the UK, and it lets sound through. It doesn't reflect it, except at the very highest frequencies. So if you make your greenhouse out of ETFE, it'll sound good too. There is, by the way, a byproduct of that. It lets sound in, but, you know, I'll let you think about that. It also sounds a bit like a drum when it rains, but we sort of bypassed that bit. As the structural engineer on the team, I said, I don't really care what we do with the structure too much, but I'd rather it wasn't outside because it's likely to be long span, and it's likely, therefore, to be steel for a sort of cost and strength ratio. And in China, it's quite an aggressive, polluted atmosphere in Beijing, and maintenance is not necessarily their strong suit while they're busy building more city than the rest of the world. And therefore, I'd rather it wasn't outside. But at the same time, inside is also the wrong place to put steelwork in a swimming pool because the chlorine used to disinfect the pool water is pretty aggressive and turns into sulfuric acid, or hydrochloric acid, sorry, and attacks the steelwork. So I said, I don't care what we do structurally, I just don't want it outside nor inside. But of course, architects also come in different flavours. It's not just the engineering disciplines that split ourselves up. So what the Americans call program architects, and I don't think there's quite an equivalent in Australia or in the UK lexicon, but those who worry about how a building should be laid out, which function goes where, they worked out that really the key to a successful Olympic swimming centre is very simple. It's to have a use after the Olympics. It's not so much about the actual competition pool hall, which is very specified, but it's putting in as much leisure facility as possible for the people of Beijing to use afterwards. So they simply maximised the footprint of the building to fill the whole site, which happened to be square, and so we had a square building. The urban designers, the people who care about how the building fits into the environment around them, they said, look, we've got this brilliant opportunity because the Olympic site, and this is a Google map of Beijing, is right on the north-south axis of Beijing that goes right through the middle of the Forbidden City and is actually the primary cultural axis of Beijing. Down to the south is the Temple of Heaven, one of the most important cultural sites in Beijing. The east-west axis is the commercial axis of Beijing. And we've got this opportunity from the master plan that was already proposed that the stadium and the aquatic centre, became the gateway from the city on this major axis into the site for the rest of the Olympics. So what they said, it's how these two respond to each other that counts. Now, these were all very well. We put all these things up on day one, and 4 weeks later we were still arguing about what we were meant to do, or what we were going to do. And the Chinese architects were drawing icebergs, I think, if I remember right, with mist curtains around them. The Australian architects were drawing waveforms. They both agreed that they wanted something that was absolutely a sort of physical manifestation of water, if you like. They thought that was the way to win an international design competition. But we didn't actually know what to do. And then, fortunately, our neighbour, the Bird's Nest Stadium scheme, was published. So they were having a competition at the same time, but a little bit ahead of us. And this winning scheme by Herzog and de Meuron, and also as Arup as engineers, came out and was put in a press. And we sat down, and I'll never forget it, 20 people sat down around a table, and we said, okay, so theirs is red and round, so we'll do a blue box. Okay? And I know it sounds sort of trivial, but it was honestly like that. And it was simply, we wanted yin and yang. So red in Chinese cultural sort of mythology is masculine, blue is feminine. Circular things speak to the heavens, square things speak to the earth. One's internally focused, one's externally focused. And at the same time, we brought all those ideas from the first day, which had been sitting in people's heads but hadn't actually been put forward properly yet, to the table. And we made it out of ETFE, and we made it an insulated greenhouse, and we made it have its natural light. And we made it sound good. So it was, again, the structure, my bit, was undetermined at this stage. But we did know we needed 2 layers of these ETFE pillows, because to make ETFE, which is a 0.2 millimetre thick plastic, it's really just a polythene bag, into something that could actually do anything, you have to inflate it with air and make it pressurised. So you make these pillows, and we knew we need 2 layers of them to keep the heat in at night. Otherwise, all the heat we gained during the day was just going to go out again during the night. So at that point, I looked at this and said, that means that there's a space between the inside pillow and the outside pillow where I can put my structure that is neither inside nor outside. And then I thought, well, how does that structure want to inhabit that space? It's not a question we normally ask. We normally ask, how does structure enclose space for human habitation? How do you build walls and roofs and things? I suddenly thought, how does structure inhabit space? And I realised never a question ever arisen before. I'd never heard anything at university or afterwards that answered that. And then I saw this photograph, which I took to be some piece of biology, an organic material. And I said, that looks to me like structure inhabiting space. That's what we're going to do. That was a great aha moment, then followed up with a, but what is it? And how do you define it? And how do I work it out? And then the magic, 2003, was really the early days of the internet. And I found, of course, the World Wide Web can help you in all these matters. So I went out and did some research. And I found out that Lord Kelvin, in the 1890s, had asked the question, how do you subdivide three-dimensional space in the optimum fashion into equal volumes? And he came up with this thing called Kelvin foam, which is truncated octahedrons, as the optimum way of doing it. And all his friends and colleagues had a look at it, and they all tried as well, and none of them could do any better, so they sort of gave up. And for 100 years, that was the answer as to how you subdivide three-dimensional space. But it didn't look very exciting to me, and it didn't look very like my photograph either. I then found a Belgian physicist at the same time, a fellow called Plateau, was looking into soap bubbles. And actually, an infinite array of soap bubbles will also be the answer to how do you subdivide three-dimensional space, because the surface tension in the bubbles will try and minimize the surface area, which means it's the same challenge. And he had observed, Plateau had observed, that soap bubbles always come together, 3 films at 120 degrees, and at the end of a line, 4 lines come in, and they're at the tetrahedral angle of 100, and if I can remember, it's either 104.9 or 109.4. I think it's 104.9. And so I said, well, that's the answer, isn't it? All you have to do is draw those lines and keep drawing them, and in a 3D CAD model, and you'll come up with the answer. Well, of course, it doesn't work like that. Otherwise, somebody would have worked it out a long time earlier. Lastly, I found that a fellow called Professor Ware and his PhD student, Dr. Phelan, in Trinity College, Dublin, in 1993, about 100 years after Kelvin, had come up with a formation of geometry which was more efficient than Kelvin foam. And it's made of these two polyhedra you see in front of you, collected together to form the molecule on the right, which then repeats. It's mainly made out of pentagons with the odd hexagon in it. And what I found is that if I took a very large block of Ware-Phelan foam and then cut it at a skew angle, and it was cutting it at a skew angle was the clever bit, or the odd bit. So if you go across the top here from left to right, and then the middle from right to left, and then the bottom, you see how we did it. We took a block of the foam at a skew angle, we chopped out a 50-metre height of it, then on plan in the middle, we chopped out a 200-metre square box. And then on the bottom, we hollowed out the spaces, the volumes that we wanted to occupy, the actual halls inside the centre itself, and you end up with this, a wonderful structure. And this was, this was sort of really new to us, because all that was done inside a machine. It wasn't done on the back of a napkin. It wasn't done with paper and pencil. And it came out with 22,000 elements joined together at 12,000 nodes or intersections. And we said, that's it. That's what we want to do. It's going to be a structure like no other. It produces a wonderfully random pattern for the pillows to go on the surfaces, which is just what the architect liked. The only question now was, how do we show the judges that this is what we're putting forward? Okay? So we said, that's easy. We'll just make a model. Okay? Make a physical model. And actually, as you might realize by now, this isn't going to be an easy thing to make a physical model of. So we said, that's okay, because there are these things called rapid prototyping. So what we'll do is we'll make one of these wonderful models using a computer-driven rapid prototyping machine, never been used in the architectural engineering world before, but commonplace in the car and aerospace industries. But nobody had ever made a model with 22,000 different bits in it. Okay? They were used to making one piece that was a complex shape. It took us 4 weeks eventually to get our data in the right format to get the model to work. And we made this model 24 hours before the deadline for the competition. And we shipped it from Melbourne to Beijing overnight, where the Chinese had handmade the surfaces, which they glued onto the model. And I'll never forget one of them, I got a phone call saying, the north wall doesn't fit. Okay. What'll we do? And for some reason, I have no idea why, I said, what happens if you turn it round? Okay. And luckily that was the answer, and it did fit. And we made the model and submitted it, and fortunately won the competition, which is great, because we won from the jury, which are the official judges, but also the Chinese have put it on the internet for public voting. And sometimes that had happened before, and I'd normally cheated a bit and asked everybody in Arup, to vote for the Arup scheme. In this case, we won by 1 million votes, so I don't think the Arup voting system would have made much better. Then you get this incredible euphoria when you win a design competition. But of course, to win a design competition, you normally push the boat quite a long way away from the shore. And then the next day you wake up and you think, aha, now we have to make it work. Okay. So from a structural point of view, I built then an analytical model. You might think I should have done this before, but we were so busy making the physical model to convince the judges that we hadn't thought about the analytical model. I mean, it looked like a structure, It felt like a structure. If you like, it smelt like a structure. But was it one? And the first time we built an analytical model, I couldn't make it stand up. If the elements were put in rather large, to make them strong enough, they were also too heavy. And if they were put in smaller, then they were too weak and the thing fell down. So again, in this sort of brand new digital age, we invented a whole new analytical process that sorted it out for us. And what that meant, what we did is very simple. It seems trivial, but it was one of those things, one of those breakthroughs. You put every element in rather small, you analyze it, you find out the stresses in every element and compare it with literally the code of practice of China, not some arbitrary number, but the actual code of practice of China. If you didn't meet the code, then make it bigger by one small increment. Yeah? And if for some reason it seemed to be larger than it had to be, make it smaller. by one small increment. Don't try and guess the actual answer, just move it in the right direction slowly. And what we found after a lot of experiment was it would converge, as you can see here, after about 20 cycles, it converged on a stable answer, which also, I'm glad to say, proved it was also an efficient structure at about 5,000 tons of steel. This picture shows you slowly, so every different colour there is one of 10 different sizes. We only use 10 different sizes in the whole model. And you may be able to work out now why I couldn't guess which one went where. Okay. Actually, the thing is so highly redundant for the structural engineers in the room that you could come up with an infinite number of solutions that also worked. It didn't matter which one you used, as long as it would then produce a set of calculations that would satisfy the Chinese authorities that in a linear elastic state, it would comply with the Chinese code. And every time you ran it, you got a different answer, which was rather nice, you know. So every day we got a different structure. Yeah? And so we just said one day, okay, we'll have that one. Okay? Moving on. This shows you its dynamic properties. It is a completely framed structure. There's no triangulation in it. So it relies entirely on the moments at the end of each element. And what's really strange about this is these are the first 4 modes of vibration. So the top 2, left and right, not surprisingly, are very similar and have a frequency of about 1 hertz. And because it's a square thing in the end, you know, so it's doing roughly the same thing. But what amazed me is that the bottom 2, the vertical and the torsional, are the next 2 modes, and they're also around 1 hertz. I still don't know why. I can't tell you why. But what it meant was, in an earthquake, and earthquakes are the major dominant load in Beijing, every single element played its part in absorbing energy, or could play its part in absorbing energy from the earthquake. So it actually turned out to be the most earthquake-resisting building in the world, probably. I can't prove that. I can tell you it takes more than 1 gravity sideways, and it's still standing up quite easily. It just forms plastic hinge after plastic hinge after plastic hinge after plastic hinge until it gets to 44,000 of them before it gives up. Having done all the sizing of the elements inside the computer, we then wrote a piece of logic that said, well, we'll make the nodes spherical because that's an easy way of elements coming together. And we'll size the spheres according to the size of the elements coming into them. And we'll write a rule, and therefore we'll develop all the spheres as well. Then all the elements get cut back until they meet their spheres. And then we have, you know, what we now call a BIM model. We have a fully defined piece of structure. So far, it hasn't been touched by anybody. It hasn't been meddled with manually, if you like. And we got it down to, we could redo the whole structural process if, for example, we wanted to make the building smaller, which we had to do several times, or add a doorway, or do something to it, in 3 days. So we could go 3 days from changing it to having a new set of construction documents. The construction documents we could portray in lots of different ways. Up till now, I'd always said, well, there should only be 1 set of contract information for fear of there being contradiction. So it was normally the 2-dimensional drawings with the contract information. Here we said, well, actually, as this is just a set of data that hasn't been touched by anybody, then we can represent it any way we want. So we can represent it, as you see on the left here, as a wireframe model with a lot of tags on it and a whole set of data saying what each tag meant. Or we can represent it on the right-hand side as a set of 2D information, or at the bottom of the right-hand side, you can barely see it, I'm sorry, a bit washed out, but 3-dimensional views of the actual connection details, for example. And you can visualize it. So this isn't what the architects normally call a CGI, you know, an artificial, if you like, a visualization of something where a lot of work's been done in Photoshop to make it look nice. This is actually just a view of the construction documents. And it was the first time we'd done this. As I say, we're now just into 2004. But there was some magic in the original geometry, and that is that even though the tube sizes were different throughout the building, the geometry repeated because it had come from that piece of ware Phelan foam that repeated. And so we said the way to build it is to make a jig, which would always be a fixed jig, and you make up these little 4-legged elements, and then on site you bolt them together. And as long as you bolt the right ones together in the right order, you get the structure we first thought of. But the Chinese said, well, that looks a bit hard work. Why don't we just make lots of tubes and lots of balls and a big scaffold, and we welded it together. And they did. And I have no idea whether they welded the right ones to the right ones. None whatsoever. But because, actually, I say that flippantly, but because of the huge redundancy in the structure, it doesn't actually matter. You form plastic hinges wherever you needed to, and it would redistribute. You know, the strength was there somewhere, if you will. Actually, I think they probably got it right. They took it very seriously. And then eventually, a year later, they took the scaffold out, and we began to see what we had constructed. This is the inside of the leisure hall that you didn't see during the Olympics. It was still not fitted out. And then it was finished. So I was invited to the official opening on Australia Day in 2008. I got the invitation at 5 p.m. on a Friday that the official opening was going to be at 9 a.m. on a Monday. So but fortunately, I managed to get there. One of the other things we did is to get the heat and light balance right. All the ETFE pillows are covered with a silver dot pattern, but we varied the density of the dot pattern according to how much light and how much heat we wanted into that particular space of the building. So you can see here that when the light's behind the building, you see through it. You get some transparency. And here again, the same thing. But as the sun comes round onto the face of the building, it goes this incredibly metallic colour instead, because now all you're seeing is the silver dots, you know, reflected back at you and such. So it's a bit like the Sydney Opera House. It changes its mood and its feeling according to the lighting conditions and what you get before it, which wasn't something, I must say, we totally predicted. But it was still quite nice. And then we went inside. And inside the main pool hall, we're actually only getting 5% daylight, because the television companies wouldn't let in more than that. If they said, if it's any more than that, we'll black it out anyway and use our floodlights, because they're worried about controlling light for television. A bit like our cameraman at the back who's spotlight me to make sure I can be filmed. But it's a similar sort of thing. But actually 5% daylight is tons if you're inside, if you see what I mean. It feels as though you're in natural light, in bright light. This, I think, was my favourite space. This was just a cafe in one corner, but it had a real sort of serene, calm feeling, almost spiritual. And this is Mr. Phelps winning his 7th gold medal. 45 world records were broken in the swimming centre in Beijing. And I, to this day, I will uphold the idea that it was because it was such a beautiful place to be that caused the athletes to perform so well, and it was nothing to do with the sharkskin suits that they were wearing. And then this is the bit you didn't see at the Olympics. This is the leisure centre. So this is the legacy. This is what the people of Beijing get to use every day now. At one time, the Beijing government said, actually, we don't want to make it into a leisure centre. We'd rather make it into a posh restaurant because we think it's so good that it should be very expensive to go into. And we pleaded with them that we would much rather it were for the people of Beijing, and they acquiesced, which is great. So there we have it. The two form this gateway. I think if you think about the Olympics, I don't think you remember any other buildings really than these two. There's actually a building right next door, the main convention centre, the main indoor arena, which is larger than either of these, but you probably can't remember what it was. So I've got 3 slides in amongst these talks about projects, sort of pointing out some I guess some of my approaches to life or approaches to design. So the first one is, at Arup we say we shape a better world. That's our strap line, if you will. But what do we mean by that? And for a long time I thought, well, it actually just means we've got to make the world sustainable. Now, I don't back down from that at all. We do have to make the world sustainable. But sustainability is a lot about reducing impacts, reducing environmental impacts, reducing financial costs, reducing social impacts. That could produce many different worlds, actually, that comply with that. And which one do we actually want? So what about the benefits? What are we actually trying to do as well as being sustainable? And in my view, it's about improving the world for people. And there are tons of different levels you can look at that. Make people safer, make them healthier, give them more functionality, more amenity. But ultimately, it's also to inspire them. We want to enjoy life, surely. We want our built environment to be pleasurable, to be delightful. So in the end, I short-circuit all of that and say delightful efficiency. Delightful, maximise the benefits, efficiency, minimize the costs, whatever they might be. So this building I've already introduced to you. This is the Bird's Nest Stadium in Beijing. When I look at that, I have no doubt at all that it's the most beautiful stadium ever built in the world. But unfortunately, it was also quite expensive. It uses an awful lot of steel to make it work because it is a sculpture with a structure to hold it up, if you will. It is not really made by intense collaboration between engineer and architect trying to work out how to do both at once. So I sat down with my best friend, Philip Cox, and did this competition for a stadium in Durban for the World Cup, the Soccer World Cup. And you might notice that it never got built. It wasn't part of the World Cup. I still haven't got over losing this one, so I'm going to tell you about it instead. Okay? So this is about how an engineer and architect can try and come together and trust each other enough to try and work out how a form will work both as structure and architecture. It's a pretty intense and trusting sort of arrangement because, particularly for Philip, he has to trust me that when he comes up with something he likes the look of, and I say that doesn't really work as a structure, that I'm right. And that I'm acting in his best interests and genuinely trying to find something that will work as a structure and look the way he would like it to look. So anyway, after a while, we came up with what we thought was a really beautiful building that also worked highly efficiently. And I'll just for a moment describe how it works. So if we were to work like the Bird's Nest Stadium, which are really just these big deep trusses spanning across it, this is a cross section, and it shows something like a 9-metre deep truss cantilevering 70 metres. And it shows you've got tension in the top chord and compression in the bottom chord under a vertically downwards load. But when you do that in 3 dimensions, you have to put them, sort of 12 metres apart or thereabouts. You have to put spanning elements between them to hold up the cladding. You have to keep the compression cord stable laterally, so you add another layer of structure at the bottom. It's now looking pretty nasty, so you probably add a ceiling underneath, which indeed the Bird's Nest has. And you end up with a lot of steel and a bit of a jungle. If instead you take exactly the same principles and smear them out into 3 dimensions, and now you offset the bottom chords from the top chords, you can now have a structure where all the structure is carrying the cladding, where the structure is also auto-stable. That is, the difference in curvature and the offset keeps everything from buckling. And you literally take out 60% of the weight by going from the truss structure to this one. And in our case, the brief was for a stadium that could hold 70,000 for the World Cup and then go down to 50,000 afterwards. And we could put the 20,000 extra seats up into those humps in the roof that wouldn't have been available to you if you'd done a truss with a ceiling on it. So I'm still... Oh, and the last bit, of course, is the inwards curvature of the walls, which was part of what we wanted it to look like, also gave you exactly the right amount of floor plate at each level for that particular stadium brief. Often in stadiums, you get a problem that the floor plates get bigger and bigger as you come down, but actually there's no more facilities that you need at the bottom than you need at the top. But as I said, unfortunately, we lost that one. But instead we did the baby brother. Okay? This is AAMI Park in Melbourne. I love this photograph of AAMI Park because it looks like a CGI, but it's not. It's the real thing. This is what we built. The principle's the same. It's a much more modest design. It's only a 25,000 seat stadium with a small roof. But what we did do is use parametric modelling to help us make it as efficient as possible. So on the left there, you see a program called CATIA, and the red line links the leading edge of the roof together. And all the white lines are rule-based and follow the red line. So we've set up a whole lot of geometrical rules that operate from the red line. So we adjust the red line a bit, and we mill, the structural model pops out, we size it automatically like we did at Beijing, using the same piece of software. The architect gets to look at it and says, do I like it? Do I not like it? Does it look better? And we also looked at the panelisation of the facade, the cladding. Are we getting more or less repetition? Is it more efficient to clad it with this shape or the other shape? In theory, you could link all these together and use some kind of genetic algorithm to sort out the most optimum solution. In reality, I find it's better to do it by hand, actually. to adjust the red line, look at the different outcomes, and then think about how else should you adjust it to make it better. You know, which is more important? Making it look good, making it repetitious, making it less steel. And eventually we decide on something. The other advantage, as I said before in a way, is that this is a CGI. This is a rendering, you know, we made of the building before we built it, and this is the building after it was constructed. So you get a pretty good idea now what you're going to get before you go into the physical world. Here we see it being used, and this same idea of the seats in the humps. In this case, we likened it to a club, you know, where you might sit in your booth at the back. You might have your favourite piece that you always go to, that you occupy. You know, it breaks up. The inside of stadiums can be quite characterless. They all look the same once you're in them. You know, we make them different from the outside, not necessarily from the inside. This, again, is one of my favourite shots, because, again, this is reality. This is it, sitting on the river in Melbourne. And then lit up at night. Another thing, Melbourne is fantastic because you'll be able to, here as well, you can see your stadium from the city. You can see what's happening. You can decide, you know, am I going to go and watch a match tonight as you come out of work? You know, or am I just going to go and have a drink there? Or am I going to, you know, walk around the park? It's a great place. So here's my second little sort of philosophic piece, and that's about design. When I was first made an Arup Fellow 10 years ago, the first question I was asked is, okay, so how do you do it? And I shrugged my shoulders and said, well, I don't know. You know, it's what I do. I'm not an academic. I don't think very much in those sorts of ways. I just, you know, do what I do. And so it made me think. You know. And so sort of 3 or 4 years later, I decided, I think, that this is the way I tend to go about a project. You know. The first thing is to think about what do you want to achieve, not as a structural engineer, but what should the project achieve? What outcomes does your client really want? It's often not written in the brief, actually. You often have to go and talk to people to find out what they really want. And also, of course, stakeholders. It's not just about what your client wants, but what do the end users want? What does the community want? What do people overall want? The second one is a sort of what I think of as design actually being, is to challenge the status quo, to not accept that what's been done before is the best that can be done. It may be, but you don't accept it initially. You first say, can it be done better? And it doesn't matter what it is. It could be a spreadsheet. It could be a project management plan. It could be how you write an email. It doesn't matter. All of those things, when you do them, can they be done better? The third one, as I've said before, is trying to improve people's lives. And in particular, I think to get an emotional response at a human scale. I remember I worked for a wonderful engineer called Peter Rice when I was young, who unfortunately died young, like George, I guess. Peter said to me, though, he said, Tristram, it doesn't matter if your structure is wizardly and wonderful. What matters is how people will respond to it. How will they think? You know, what emotional response will you get from people who visit it? Okay. So then, as I've already said, you make it as efficient as you can. You make it as delightful as you can. And lastly, and most importantly for us in our industry, you have to deliver it. It's no good it just sort of ending up like Durban did, you know, in the ether. It has to come out and become real. And that's the hardest challenge of the lot. It has to be built. So this project, I was asked to include some more international projects. So these are projects I've been working on recently that haven't always been completed. So this is about an airport in Kuwait with Norman Foster as the architect. And the question here is, what actually are you trying to do in Kuwait? What's Kuwait about? And Kuwait's about heat and dirt, or dust, desert storms. It's about solidity and trying to find shade and the feeling of shade, even when it's not, or the feeling of coolth, rather, that comes from shade, and mass and masonry. And this is a plan of the airport superimposed on Hong Kong's harbour. So it wasn't a small challenge that we were faced with. This airport is 1.2 kilometres from tip to tip as a triangular element. Yet, Fosters, in their wisdom, decided it should be made of concrete. So we were faced with a challenge of this is just one arm of it, of a concrete roof, probably 10 times larger than any other concrete roof that has ever been built, with up to a 60-metre cantilever around all its edges, and a 48-metre span between it. And then how do you do this efficiently? So we came up really with a schema you see in front of you, that the bottom is a set of arches and ribs out of post-tension concrete, so if you like the Opera House construction, or bridge, big segmental bridge construction. Then on top of it, the idea of this lightweight concrete shell. But the lightweight concrete shell is not easy. In situ concrete, it would be 300 millimeters thick, which would actually weigh an awful lot. You'd have every single panel is different, I should have said, all the shells are different. So the formwork would have been horrendous, and then it would have fallen apart under thermal loads because it's so big. So in the end, we came up with this idea of using fruit boxes, we call them. So we call this fruit box engineering. And it was simply the idea, if we make panels of, and I call these concrete panels for Foster's sake, but for me they're hybrid panels because they're steel frames with a concrete base. All the steel is vertically set in real life and flat and laser cut, so to get them as accurately as possible. 4 pieces. Then we put them on a formwork and we cast the piece of concrete in the bottom. And then as you see at the bottom there, you produce these cruciform elements, also from laser cut steel, which you then just bolt everything together. And in theory, it'll all work, as long as everything is made accurately. And this is an image, therefore, of the central piece, probably the simplest bit of how it would all go together. Each piece is about 4 meters square, the fruit boxes, to give you a scale. And the concrete is only 130 millimeters thick. And that shows you the more complex piece around the edge with the 60-meter cantilever. But it was applying a ruthless piece of logic, if you like, a piece of process across an analog idea. Here's a fruit box, and this is its clever bit. The clever bit is that concrete will carry quite a lot of compression, as I think we all know, and therefore in compression it all sort of forces itself together if it gets hot. But if it starts pulling itself apart, the concrete won't take much tension. So what happens though is that the steel side plates flex and bend and allow it to go away. So it was all about balancing stiffnesses. How do we get the right amount of in-plane stiffness so the shells worked, the right amount of bending stiffness so they stayed stable and didn't buckle in compression, but the least amount of tension stiffness so we could release the tension forces out of the concrete. And it was quite an ask, and we ended up doing full not dynamic, but using a dynamic nonlinear program to analyze, as you can see at this level, every bar of reinforcement, all the welds, all the steel, and in a nonlinear fashion pulling it and pushing it and bending it, just to make sure that all those stiffness parameters were actually what we were going to get. And there you see an image of the final product. This is only out to tender as we speak, so hasn't yet been proven to work. This is, but it has been fully designed. Second to last is the Singapore Sports Hub. So this is a stadium for Singapore. Singaporeans are not known for being sports fans, but they wanted a national stadium for their national identity. So it had to be a multi-purpose stadium. So one of its attributes is it has an opening and closing roof, so you can use it in the rain, and also so you can keep people cool in the heat of the Singaporean summer. The scheme, this is Arup as architects and engineers. So the scheme we came up with is this enormous dome that clear spans across the seats, that provides a moving piece at the top, a solid piece out to the edge of the seats, and then an open louvered piece at the perimeter. And again, to give you scale, this is a 300-meter diameter dome. I'm told it's the world's largest dome. I haven't done my own research, but I'm told it's the world's largest dome. And of course it can be open, so you can use it either in closed mode or you can open the roof, as you see here, which, just remember that shot, because the structure I'm going to talk about later is highly dependent on this problem that you've got a big weight that can be in the center or it can be separated. And then these naturally vented spaces at either side. So to keep people cool in summer, we provide under-seat air conditioning, if you like. But we're not going to try and air condition the whole volume. It's enormous. We're just going to try and produce local cooling. To do that, though, and at the bottom there, I've got a picture of a CFD, computational fluid dynamics, of all the people in their seats on the left. Then the middle image is the bottom tier. The next to the right is the middle tier, and the far right is the top tier. And what you can see in the far right is it's beginning to get warmer And the reason it's beginning to get warmer is there's radiant heat coming in through the roof. Okay, so the critical part for the fixed roof is to insulate it as well as possible and to reflect things. But the critical thing for the moving roof, the top bit, is to make it as light as possible. It's because it's this moving load that will crucify the fixed roof otherwise. So it's this delicate balancing of everybody in the room talking about what do we want out of each component and how do we make it work. So the moving roof is actually clad in ETFE like Beijing to keep it as light as possible. And then the outside is louvers for just shade for the external concourses. And this is a rendering of the outside, so you can see these components. So you can see that the pillowy shape is the ETFE clad moving panel. Then the triangular shape, if you like, with the lines across it is the fixed roof, which is Calzip aluminium cladding with a lot of insulation underneath it. And then the louvers down below for the external concourse. And this is the primary structure. But it's not the whole trick. This is part of the primary structure. So it's trusses. The trusses vary in depth and width from the center of the building, where they're deepest, to the perimeter of the building, where they're shallowest. And this comes back to this human reaction bit, which I'll talk a bit about later. But there's also these big diagonal trusses, and you're looking at it probably and thinking, well, why are they there? Well, at the bottom of all these trusses is a ring beam that holds it all together. All the sphere is in compression, the ring beam is in tension. But the ring beam cannot cope with out-of-balance loads. It can only cope with a uniform pressure pushing outwards on it. Yep? And what the diagonals do then is as this moving load changes, it redirects the moving load outwards. So when the roof is open, it pushes towards the ends. And when the roof is closed, it allows the stresses to come down in the middle. That's quite complicated. I haven't got a decent image to show you, but I hope you'll get it. And then across that, there's a set of secondary trusses and then a set of louver trusses. Lots of different geometries being used in different places to get different responses or different impacts. And of course, here you see that moving load. That's the moving roof in its open position. The secondary trusses aren't shown, otherwise it would just look like a jumble of lines. And this shows you the deflections of the roof without the moving roof shown in some of the images and with it on the top right. But you see the top left is the deadweight deflection of the whole roof without the moving panel. The top right is what the moving panel does to it when it's closed. The bottom left is what the moving panel does to it when it's open. And the sections in the bottom right show you that difference. So it goes down in the middle when it's closed and it goes down on the sides when it's open. And that was the thing that was really challenging about this roof. And here you see the louvers now complete, the louvered zone down at the concourse. And now I hope you see the benefit of tapering the trusses. They're now only 2 meters deep at the perimeter. They're 5 meters deep for buckling reasons up at the top center to carry the moving panel. But this brings them down to something that's more of a human scale where people get to meet them and interact with them. And here you see the whole structure. Last week, the fixed roof was completed and depropped. So we've now got the world's largest dome now actually exists. And this is my last slide, which is about the impact of IT in the built environment. You might have noticed I've talked quite a lot about the virtual world. I think this revolution, even though it's been going on all my life, my professional life, has still got a long way to run. The impact that the digital world has on the physical world through our ability to now design things absolutely perfectly before they're constructed. It used to be that every building was its own prototype. You only tested it when it was made. And in those days, the car industry made physical prototypes and crash tested them against solid bits of concrete. Nowadays, both of us can do it in the virtual world without resorting to the physical world. And we know what we want before we build it. I would then suggest that construction will become more like manufacturing, where we make things in factories all over the world and bring them to site and assemble them, because we know what we want. We can predetermine it. One of the reasons we pour concrete into timber forms on site is to get it right on the spot, to alter things as we go, to make the holes required for the services to pass through the structure. But all of that can now be predetermined. We can coordinate it all in the digital world. I could talk more and more about this, but I won't do too much because I'm probably out of time. And in the end, it's the Internet of Things. Out there in the physical environment itself, you can have actuators and sensors, so you can get feedback from what people are actually doing, and you can change the physical environment in real time. This is most readily seen in smart infrastructure, so the idea you can control traffic systems according to traffic flows, you can control energy supply according to energy demand, etc. And lastly, if we were clever designers, we would take all this feedback and use it to make our designs better and make our plans better. At the moment, I'm ashamed to say, most designers, when they've finished a building, walk away from it. They very rarely go back and find out how it's actually used and whether its occupants actually like it, because the myth is almost always better than the reality. So we stick with our ideas, our concepts of what we want to have happen, rather than finding out what really happens. This is the last building, last project. Back in Australia, this is in Brisbane, this is 111 Eagle Street, and it's the tower in the middle I'm going to talk about. And we put it between two very, very good, very beautiful buildings by Harry Seidler, two modernist buildings on the left and the right. This is on plan, the two grey blocks are the two existing buildings, and our site was right on the middle, but it was sitting right on top of the existing car park and right over the existing loading dock, which you can just see with a car in it right in the middle of this slide. And so we said, well, either we just, we sterilise the whole basement and site while we carve it up, build a new basement, and build our building on top, or we make use of what we've got. We leave the loading dock where it is, we put our columns where we can through the building, we put our new core where we can, which is offset to one side because of the existing loading dock, and then we make a virtue out of it and see what we can do. Unfortunately, when the core's off-centre like that, it no longer works for a 40-storey building in a cyclone zone to take the wind loads alone. So we decided we also then had to have a perimeter structure to make the building work against wind loads. So what we did is we said, well, if we start with a random position of columns, in other words, we only put them where we can, then why don't we just grow them randomly up the building? And let's see what that looks like. And actually, it occurred to me that if you incline columns very slightly, they'll actually probably work to carry the wind load as well. And so that's precisely what we did. We wrote a computer program that would generate random numbers and produce random sets of columns. It's not quite as simple as that. What we said is that from every level, let's generate a new set of columns, and then let's test it. Let's say, do we have as many columns leaning to the left as the right? In other words, is it balanced under vertical loads, rather than wanting to fall over one way or the other? Is it balanced front to back? Is it balanced torsionally? More importantly, does the floor above get a decent amount of support, or do the edge beams get too long? And we said we limited that. We said we want only an 8-metre edge beam. And then we played with the amount of randomness as you went up the building. So what happens is each time it gets to a floor, it generates a set of columns. It says pass or fail. Only 1 in 10,000 would pass times, and then it goes and generates another lot, another lot, another lot. And it might get stuck part way the building, so actually I can't find a new set of pattern of columns. It takes the next lift, in which case just go back to the bottom and start again. It's incredibly profligate. Only 1 in a million attempts actually comes out with success. But it doesn't matter, because it only takes minutes. And then you say, okay, that's one, there's one, I put it on the shelf. And when you get 20 of them on the shelf, you go down to see your friendly architect, again Philip Cox in this case, and say, do you like any of them, Philip? Do they look any good? And he normally says no. And so you come back again and you rewrite the program to some slightly different logic. And as you can see, this is the final one. And what we've done is make the columns get more random, more chaotic, more excited as you get to the top of the building, because they're carrying less load by then, so you can. Down the bottom, they're quite strict. They're quite vertical. They're quite, they've got to have a 5-degree average lean to take the wind load. After that, they can be, more upright. This is the Cox drawing of the same building, I'm glad to say. And here they've colour-coded the columns according to their size. So you can see in a way that it does actually work. The columns are behaving the way we'd expect them to. And for the structural engineers, this is on the left, the vertical load diagram. On the right, the wind load diagram, showing that the columns are doing what they're meant to do. They carry more load as you get towards the bottom, relatively evenly. And on the right-hand one, they're barely going into tension on one face, and they're taking the compression on the other. This is my favourite drawing, I think, because this is 2008. On the right is our Revit model, and on the left is the architect's Revit model rendered. And for once, they are the same thing. Okay? Only time in my life so far. We'll get there. And here it is built. Here it is in Brisbane. It was the only high-rise building in Australia to not stop construction in 2009. GPT, our client, had the courage to continue. And by the way, we were open with them in the design competition. We said, we think this is a building you'll like. It'll cost you $6 million more. Right? And they said, okay, we'll have it. Okay, we'll do it. They've done it. It was fully tenanted when it was opened. Okay, so they had the courage of their convictions to continue construction through the recession, or the modest hiccup we had in Australia. I think now we might be having a recession, unfortunately. And there it is, lit up at night. So there, ladies and gentlemen, thank you very much.
The title that Tristram chose was Unique Designs, the Power of Multidisciplinary Collaboration. I think you'll agree that the lecture demonstrated that. It was, I believe it is an inspirational lecture, entirely in keeping with George Hondros' legacy of inspiring. It's the kind of thing I think that is the reason many students choose to do engineering. The possibility, however slight it may be sometimes, of working on projects like that and be able to create some of those structures you've seen, it's truly inspirational. So thank you very much, Tristram.